Article 334.80 addresses overcurrent protection for conductors. Overcurrent protection for conductors must be provided in accordance with 334.10 through 334.14 and 334.40. Conductors must be protected against overcurrent in accordance with their ampacities as specified in 310.15 and other articles of the Electrical Code. There is an exception regarding conductors used as taps as covered in Article 210, Part Roman II, which must be protected in accordance with 310.15b16 based on their ampacities as specified in 310.15 and other articles of the Code. 334.80 discusses conductors in parallel. Conductors connected in parallel are considered as a single conductor for the purpose of applying the provisions of this section. 334.80b addresses conductors located in raceways. Firstly, feeder and branch circuit conductors, except grounding conductors, located within a raceway must be protected against overcurrent in accordance with 334.10b. Secondly, conductors within a raceway must be protected against overcurrent by either of the following. The overcurrent protective device protecting the conductors must be rated or set to trip at a current value not greater than that specified in 310.15 cone for the largest conductor in the raceway. Or B. Each conductor within the raceway must be individually protected by an overcurrent protective device rated or set to trip at a current value not greater than that specified in 310.15 cone for the conductor. 334.80c addresses conductors not in raceways. Conductors not located within a raceway must be protected against overcurrent in accordance with 334.10a. 334.80d discusses conductors protected by supplemental overcurrent protection. Conductors protected by supplemental overcurrent protection must be identified and marked in accordance with the requirements of 110.21b. 334.80e addresses conductors used as neutral conductors. Conductors used as neutral conductors must be protected against overcurrent in accordance with the provisions of 334.13. In more detail, let's discuss 310.15, which is referenced throughout 334.80. 310.15 covers ampacities for conductors rated 0 through 2000 volts. Ampacity, as defined, is the current in amps that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. The intent of 310.15 and its associated tables is to ensure conductors are not subjected to currents that will cause them to overheat, leading to insulation degradation and potential fire hazards. Several factors influence the ampacity of a conductor. Firstly, the conductor material. Copper and aluminum are the most common conductor materials, each having different conductivity and temperature ratings. Copper generally has a higher ampacity for a given size compared to aluminum. Secondly, insulation type. The type of insulation surrounding the conductor determines its maximum operating temperature. Common insulation types include THHN, THW, THWN, and XHHW, each with different temperature ratings, such as 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. Thirdly, ambient temperature. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thus lowering its ampacity. Fourthly, the number of conductors in a raceway or cable. When multiple current-carrying conductors are bundled together, the heat generated by each conductor can raise the overall temperature, requiring ampacity rating. 310.15b specifically addresses ampacity correction and adjustment factors. These factors are applied to the base ampacity values found in tables like 310.15b16 and 310.15b17 to account for ambient temperature and the number of conductors. For ambient temperatures other than 30 degrees Celsius, correction factors are applied. For example, if the ambient temperature is higher than 30 degrees Celsius, the ampacity is reduced. If it's lower, the ampacity can be increased, but this is generally not permitted for conductors used in service entrance cable SE cable applications due to the 60 degrees Celsius termination requirement. Adjustment factors are used when more than 3 current-carrying conductors are in a raceway, cable, or earth. These factors reduce the ampacity based on the number of conductors. For example, if there are 4 to 6 current-carrying conductors, the ampacity is reduced to 80% of its original value. If there are 7 to 9 conductors, it's reduced to 70%. Now, focusing on the exception mentioned in 334.80 concerning tap conductors and 310.15b16. Tap conductors are short conductors that branch off from a main feeder conductor to supply power to specific loads. These taps are permitted to have a lower ampacity than the main feeder under certain conditions, provided they are protected from overcurrent. 310.15b16 provides specific rules for these tap conductors, allowing them to be protected by the overcurrent device protecting the main feeder if certain conditions are met. Typically, this involves a tap conductor being no more than a certain length and having an ampacity that is at least a certain percentage of the overcurrent device rating. Now, let's delve into 334.10, which is referenced in 334.80b concerning conductors in raceways. 334.10 outlines the uses permitted for Type SE service entrance cable. Type SE cable is primarily used for service entrance wiring, connecting the utility service drop to the building's main service disconnect. 334.10 covers SE cable without a final overcurrent device. In this configuration, the entire length of the SE cable is considered part of the service entrance conductors and must comply with the requirements for service entrance conductors. 334.10b covers SE cable with a final overcurrent device. Here, the SE cable is permitted to supply branch circuits or feeders from the service equipment. This section refers back to 334.10 through 334.14, which further specify the installation and protection requirements. Now, elaborating on the requirements for conductors in raceways as outlined in 334.80b. When conductors are installed in raceways, the NEC requires specific attention to overcurrent protection to prevent overheating and potential damage. 334.80b states that feeder and branch circuit conductors, except grounding conductors, within a raceway must be protected against overcurrent in accordance with 334.10b. This means that the overcurrent protection must be sized to protect the conductors based on their ampacity as determined by 310.15 and other relevant articles. 334.80b2 offers two options for protecting conductors within a raceway. The first option, 334.80b2, states that the overcurrent protective device protecting the conductors must be rated or set to trip at a current value not greater than that specified in 310.15 code for the largest conductor in the raceway. This means that if there are multiple conductors of different sizes in the raceway, the overcurrent device must be sized based on the ampacity of the largest conductor. 310.15 code provides the allowable ampacities for insulated conductors rated up to 600 volts, typically used in residential and commercial applications. The second option, 334.80b2, states that each conductor within the raceway must be individually protected by an overcurrent protective device rated or set to trip at a current value not greater than that specified in 310.15 code for the conductor. This means that each conductor has its own overcurrent protection, such as a fuse or circuit breaker, sized to protect that specific conductor. This approach is common in industrial settings or where individual circuit protection is desired. Let's clarify the difference between overcurrent protection and overload protection, as they are related but distinct concepts. Overcurrent protection refers to the protection of conductors and equipment against excessive current, regardless of the cause. This includes both overload and short-circuit conditions. Overload protection specifically refers to protecting conductors and equipment from currents that exceed their rated ampacity but are less severe than a short circuit. Overloads typically occur when equipment is drawing more current than it is designed to handle, causing the conductors to overheat over time. Short-circuit protection, on the other hand, is designed to quickly interrupt very high currents caused by a fault in the circuit, such as a direct connection between a hot conductor and a neutral or ground. Fuses and circuit breakers are the most common types of overcurrent protective devices. Fuses are one-time devices that melt and interrupt the circuit when the current exceeds their rating. Circuit breakers are resettable devices that trip and interrupt the circuit when the current exceeds their rating. They can be manually reset after the fault is cleared. When selecting overcurrent protective devices, it is crucial to consider the interrupting rating, which is the maximum fault current that the device can safely interrupt. The interrupting rating must be greater than the available fault current at the point of installation. Available fault current is the maximum current that can flow in a circuit under short circuit conditions. It is determined by the impedance of the power source and the circuit conductors. Ignoring this can lead to device failure under fault conditions. Here are some examples illustrating how to apply 334.80 in various scenarios. Firstly, a service entrance cable SC cable consisting of 3 number 6 American wire gauge AWG copper conductors with THHN insulation is installed from the service drop to the main service disconnect. The conductors are rated for 75 amps at 75 degrees Celsius per 310.15 B16. The overcurrent protection must not exceed 60 amps due to the 60 degrees Celsius rating as required by 338.10 B4 and 334.80. Secondly, a feeder circuit consisting of 4 number 12 AWG copper conductors with THHN insulation is installed in a raceway. The conductors are rated for 30 amps at 90 degrees Celsius per 310.15 B16. However, since there are 4 current-carrying conductors in the raceway, an adjustment factor of 80% must be applied, reducing the allowable ampacity to 24 amps. The overcurrent protection must not exceed 20 amps, as per the next standard size rule in 240.4b. Thirdly, a tap conductor consisting of number 14 AWG copper wire is tapped from a number 6 AWG feeder circuit. The tap conductor is less than 10 feet long and is protected by a 20 amp overcurrent device on the main feeder. According to 240.21b, the number 14 AWG tap conductor is permitted because its ampacity is at least 1/3 of the overcurrent device rating. Now, let's provide additional insights on selecting and installing SC cable to comply with 334.80 and related articles. Firstly, always verify local codes and amendments. Electrical codes can vary by jurisdiction, so it's essential to verify the local requirements before starting any electrical work. Secondly, use the correct size conductors. Select the appropriate conductor size based on the load requirements, voltage drop calculations, and ampacity ratings. Use the appropriate tables in the NEC to determine the correct size. Thirdly, properly terminate conductors. Ensure that all conductors are properly terminated and tightened at the connection points. Loose connections can cause overheating and arcing, leading to potential fire hazards. Fourthly, protect cables from physical damage. Protect cables from physical damage by routing them through conduit or using protective covers where necessary. Avoid running cables in areas where they are likely to be damaged by impact or abrasion. Fifthly, use approved fittings and connectors. Use only approved fittings and connectors that are listed for use with the type of cable being installed. Ensure that the fittings are properly installed and tightened to provide a secure connection. Sixthly, follow the manufacturer's instructions. Always follow the manufacturer's instructions for installing and terminating cables and fittings. This will help ensure that the installation is safe and compliant with the NEC. Seventhly, consider future expansion. When designing electrical systems, consider the possibility of future expansion and install additional capacity as needed. This can help avoid costly upgrades in the future. Eighthly, perform regular inspections and maintenance. Regularly inspect electrical systems for signs of damage or wear and tear. Perform maintenance as needed to keep the system in good working condition. A summary of key considerations includes understanding conductor ampacity, which involves calculating the ampacity of conductors based on their size, insulation type, and ambient temperature. Ensure that the overcurrent protection is properly sized to protect the conductors and equipment. Select appropriate overcurrent protective devices. Consider the interrupting rating and coordination with other protective devices. Lastly, always follow the requirements of the NEC and local codes. Properly installed and maintained electrical systems are essential for safety and reliability. The information provided here is intended as a general guide and should not be considered a substitute for professional electrical advice.